Nice easy circle question. Obviously in this particular case they're expecting you to use radians, but obviously the thing with circles, and only loonies can draw perfect freehand circles, so I'm going to take the American Fifth Amendment on that and not draw one on the grounds I might incriminate myself. So the thing with circles is that we accepted years and years and years ago that C was equal to pi d, or 2 pi r, and that the area of a circle was pi r squared. And that's what we learned when we were quite young, key stage 3 sort of. And the problem there was this irrationality of pi. Pi, of course, is not a nice easy number. It's tacky, it's irrational. There's the issue. When we got better at GCSE, we got the length of a sector of the circle, or the length of an arc of a circle, and that became 2 pi r theta over 360, which if you wanted to cancel gives you that one, and that the area of a sector was pi r squared theta over 360, because they were fractions of the full circle 360. Now we use 360 simply because it's a really nice number. You think of all the factors that 360's got that go into it, works fantastically. The definition of a radian, of course, is that if you've got a circle, a radian is the angle at the center when the arc is exactly the same as the radius of the circle. And so it actually works quite well that 2 pi in degrees, or 2 pi radians, is exactly the same as 360 degrees. Now there's the key building block, because of course if you can replace your 2 pi, so what we reduce our formulae to are, instead of being 2 pi r theta over 360, if I reduce that to 2 pi because they're the same, it becomes that my length is equal to r theta, and that my area of my sector, pi r squared theta over 2 pi, means that I eliminate the pi's and my area becomes 1/2 r squared theta. So those in radian measures, as long as I'm measuring in radians, and I use little c for circular measure rather than the little circle for degrees, that makes my life really easy. And I suppose it might have been worthwhile teaching these in the first place. Okay, so in this particular case, I know that my radius is 4, and I know that the length of the minor arc in this particular circle is 5 centimeters. So I've got that the length is equal to 5, that the radius is equal to 4, and fairly obviously in this particular case, because I want to find the angle, and I don't really even need to rearrange it. Angle will be length over the radius, which is 5 over 4, and if you want to write that as a decimal, that's up to you, but I would leave that at 5 over 4 radians. Okay, no real problem. My next part of the question is determine the area of the sector. Now the area of the sector, as I've just said, is 1/2 r squared theta, as long as theta is measured in radians. In this particular case, we know that the radius is 4. We know the angle is 5 over 4 because we've just measured, or just calculated that. So my area is quite happily going to be 1/2 multiplied by 4 squared multiplied by 5 over 4. Okay, and so clearly I've got 4 squared is 16, half of that is 8. 8 times 5 over 4 will give me 10. It doesn't really make any difference. I think I'd be tempted to do a little bit of cancellation Half of 4 is 2, and 2 times 5 gives me 10. So the area of that is 10 square units. Then I would put in centimetres squared. But the beauty of this technique is that, of course, it makes the actual calculations really easy. You think about the difficulties that younger students have with pi and its irrationality, 3.1415926, etc. And circle work becomes really hard because of that. Maths should be about making life really easy, not about making life hard.
For a little addition to the question, we can look at a sector of a circle, and we can think about the triangle that we form. So if this is theta and this is r, then what's the area of the triangle? Well, this is r as well, so we can use area equals a half AB sine c. And in this case, we have a half times r times sine theta. So that's a half r squared sine theta. So that's the area here. So if we want to find the area of this bit here, then we have that is equal to the area of the sector take away the area of the triangle. So that gives us a half r squared theta minus a half r squared sine theta, which is a half r squared theta minus sine theta. Now, if we now connect this to the small angle approximations, where we have that as theta tends to 0, sine theta tends to theta, then this tells us that area A tends to 0 as theta tends to 0, which is sort of obvious, but it also means that the curve of the circle, so this bit, tends to a straight line, which is a weird sort of concept. This is a screenshot from a little Geogebra app. You can see what you would need to type in here to get this, and what you can do is you can get the point C and you can slide it round towards B. Now then, if you like, you can zoom in on this sort of portion here. If you've got a mouse, you can use the wheel, and what you'll see is the line from C to B and the arc from C to B getting closer and closer, and at some point it's almost impossible to see that the circle is actually curved. Worth a look.